I will also do a short introduction before, and then I will pass you the floor. Okay.
And Rodrigo, can people interrupt with questions if they want to?
Well, that's if you prefer. Usually, what we do is in the end, people ask questions, but if you prefer, I can tell people.
I actually prefer if they ask questions immediately. Yeah, that's fine.
Okay. Very well. Well, people are still joining, but I think we can start. Okay, so let us start. Hello, everyone. Welcome to another talk in our webinar series. Today we have Robert Nikutta from the NOIRLab talking about Astro Data Lab, that is an open access and open data science platform. Before we start, a quick reminder. So this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA and CTI. If you want, you can interrupt and ask questions during the presentation. If you're on YouTube, you can write your questions in the comments section and I will read it to Robert, okay? So Robert, thank you very much for being with us today. The floor is yours.
Thank you very much, Rodrigo. Thank you very much, everybody, for the opportunity to talk to you. I'm very pleased to be talking to my friends and colleagues from LIneA. We've been working together over the years, for instance, on the DS collaboration. So I know some of you. So thank you for the opportunity. Also, slightly belated congratulations on the 10-year anniversary, recent 10-year anniversary of LIneA, and the great workshop that you have organized, which I participated in. It was really nice. So I'm very happy to be here today and talk to you about the project that I'm the project scientist and team lead of, Astro Data Lab. Maybe you know us originally as Data Lab or NOIO Data Lab, but recently in the last year and a half or so, you probably heard that NOIO merged together with Gemini and with the future LSST Rubin operations, not the construction, but operations when they are ready, to form a new, bigger organization called NOIRLab, which stands for, I think, National Optical Infrared Astronomy Research Laboratory. That's a lot, but we settled on a short acronym, NOIRLab, because it's mostly also nighttime observations that we run from our observatories. So that stuck, and we're happy now running with this name. I'm giving this talk on behalf of myself and the Data Lab team, of course, and I want to show you what we think a science platform is. It's more than a data archive, of course, and show you then what we do in detail to bring big data to the people. And so at any point, if you feel like you have a question, please let Rodrigo know, or just jump in if you're on Zoom, and I'll be happy to answer questions as we go. This is probably easier to do. So I'm hoping that this video presentation, this video starts playing here. Okay, let's do it again. It played a second ago. And while it's playing, I wanted to tell you something. Let's go one back. Okay, maybe now. Well, I'm sorry, it just played a second ago. It doesn't play anymore. It plays now. Okay, good. 3 times the charm. So what you see here, and while I'm talking, is the motivation to build something like a science platform is that the data that we have obtained now in astronomy regularly in the last decade or so is growing exponentially, but also both in volume and in complexity. What you see here is a rotating map, all-scan map, of the total exposure time on the telescopes that we collected from the telescopes that NOIRLab operates, and only the 2 to 4 meter class telescopes. So Gemini is not even included there. Let me try to play it again, maybe. Yeah. And so you see, we're starting in 2001, the animation, and here basically the exposure time. It's a logarithmic scale. One single exposure at 30 seconds roughly, but in the end we have thousands of seconds for some fields. And you see in 2012 and 13, when the dark energy camera turns on, we start filling out the sky with the various surveys, dark energy survey, the plane survey, bulge survey, and so on. And so by the end of 2019, almost 2020, we're filling almost 3/4 of the sky, and with very, very deep data. Some of them have hundreds of epochs of observations. So that's a growth in data volume. And the next slide I can show you. This is data from the Science Data Archive, also in Tucson at NOIRLab. So this is mostly images in our mass storage that you can access through the archive. And you see roughly in the same period from 2011 to 2020. In red, you see just a volume measured in terabytes of the raw images collected. You notice, of course, the slowdown here in 2020 when the observatory is shut down because of COVID. So we were not collecting any new data. The reduced images is growing exponentially as well, growing linearly as well, but faster than actually the data collection. And what's growing fastest in the last 5 years is here in blue, are the high-level science products, so catalogs and derived data from those measurements and from those reduced images. And so in 2020, this was growing still because people were producing new catalogs and new kind of high-level science products, even though we were not collecting any new data in 2020. So in 2020, by the end of 2020, we were over 2 petabytes of data, and this does not include any kind of calibration data or any kind of weighted masks and stuff like that. If you include them, we're way over 5 petabytes. So this is not directly Data Lab. This is just in the same building, in the same server room, but Data Lab accesses these data products, and I'll show you in a second how. So you see, this is kind of an avalanche, an explosion of data, right? Astronomy happens everywhere. And now the data have become, long ago, data have become too big for people to download directly. You can download a single image, you can download maybe a part of a catalog. But if you wanted to, for instance, download the entire dark energy survey, that would take days, if not weeks, depending on your network speed. And even bigger problem is, of course, then if you wanted to process this on your home computer or even on a work computer workstation, this is impossible, simply because of the volume and also the complexity of the data. So I want to show you first what we understand as a science platform. We call ourselves Astro Data Lab Science Platform. But what is it? If you collect a bunch of data sets, and the data set could be a single spectrum, a single image, or entire survey, catalogs plus images, right? That's one data set. If you put them in many of those in databases, you have a database you can start from. So number 2. If you go to 3 and collect, for instance, number of databases, maybe an image archive next to it, or file collections, you have a data center. And that's what many people and many organizations have. And that's what NOIO and now NOIRLab had also before 2017, a data center. If you add a little bit of interface to it, for instance, clients and services like a web interface where you can search for data in your data center, in your archive, have facilities for retrieval, for instance, you stage a download or you allow people to click a button and it downloads a catalog for them or images, and also search for data. Then you have a science archive. It's basically a little bit augmentation on top of the data center, right? But note that all the compute that happens with the data afterwards, so other than discovery, all the analysis and reduction and everything happens then at home or your home institution. So compute is outside when you have a science archive. And so the only major big difference between the science archive and the science platform, what Data Lab is as well, is if you put the compute in the same building, in the same server room, or through a very fast network connection, co-located with all the data holdings. And if you have this co-location here, the compute box here and the data center box, then now you of course can, because of this synergy, you can produce, you can build a lot of data services on top of it. So some of them here mentioned an image cutout service, cross-matching service, visualization tools, even machine learning tools, plus the old stuff that you had, retrieval, search, web interface to your data discovery, and so on. So the possibilities are limitless. And so now the user does not need a fast, big, powerful computer. They just need a network connection into your science platform, an account, and they can run computation here together with the data. So latency and transfer costs, transfer durations are small, and the costs, of course, are carried by the science platform or whatever the model is. The idea is, of course, that now, because you don't have compute at home, you instead bring your ideas and your code, your analysis code, to the data center. And so we need to provide some kind of possibility for researchers to execute code, to run programs on the science platform computers. briefly, maybe what kind of data types you can have, and these are the data types we're currently hosting at Data Lab. So of course, currently we're hosting lots of catalogs. So these are 2D tables from photometry and spectroscopy as well, but mostly photometry, where you can query for them, and you can query by schema, by table, by name of survey. You can query based on coordinates. You can query anything you can imagine, and you can also join tables, of course. We also host images and access, like I said, the images in the vast data archive co-located in the same building. So here's an example, for instance, 4 catalogs from a particular survey. And we also provide an opportunity for survey teams, when they publish a data set through us, to construct a heterogeneous data collection, which we call a file service. And it's literally anything that they want to put in. There could be the original files, the catalog files, could be auxiliary data, could be calibration data, could be even instructional documentation. It's just a collection of files in a directory, and in the way that the survey people want to have it accessed by others. Often it's this, the collection that they use internally before they publish a data set. And so we put this in the file service, give it a name, and then you can, again, in the notebook, for instance, you can create the same as a LS, the Go Green DR1 file service. This is just a particular survey made with Gemini telescopes called Go Green. And then you have all the raw files that you can access those files in a raw fashion. This one's useful if you want to repeat reduction, data reduction, and things that the survey has done before. Then now the new thing for us is spectroscopy. Since 1 year or so, we've been developing a prototype, which I will talk about a bit later in this presentation, to serve 1D spectra. Because now we're entering also the era of massively multiplexed spectroscopy, right? Where you have not just a few spectra or a few hundreds of spectra, but actually millions of spectra coming out of the arrays. And so we, as a demonstrator, we have implemented a first iteration of this spectroscopic service, where we serve SDSS data, the data release 8 through 16. And 16 is also in a fast cache, so it's really, really fast to retrieve it. I'll show you in a second. This was a demonstrator that is already public in production, but it serves, the lessons learned from this are serving into our current development of a production level spectroscopic service that can scale to the size of DESI, the Dark Energy Spectroscopic Instrument, which is operational on Kitt Peak in Arizona since about 1 month. 1 month of survey time. They have been doing survey validation the last year, and it went well. And now they're collecting data for the main survey. It's a 5-year survey that will generate, I think, something like 40 million spectra of galaxies, the deepest and widest spectroscopic survey to date. And of course, in the future, we would like to expand this to host also more complex spectroscopic products like 2D spectra, IQ cubes, and so on. But that's in the future. We haven't started any implementation on that yet. And so maybe just to reiterate, if you come as a user to Data Lab, from your perspective, you want all the data here in the blue color on the base level in the back end. You want to access the TAP DB catalogs. So these are really the spectros, the photometric catalogs. You want to access your own databases, which we also allow you to have your own file collections, but also the file services I talked about, and of course, spectral product image and so on. To access those, you only see the green layer here, which are really the client's interfaces and the APIs that we expose. So you can, for instance, for the catalogs, you can use any TAP client you want, the most popular, of course, being TopCat. You can do certain queries or many queries through a web browser. We have a query form there, although it's not the most powerful one. It's maybe for exploratory queries. But we also expose APIs and have code for that, which you can install either on your computer or directly. You can run them from the notebook server that runs on Data Lab computers. So of course, you have the benefit of co-location. And there's also a tool for command line if you want. So you can really submit queries on the command line and it comes back as a stream of CSV formatted strings. And so in the middle, of course, there's the intermediate layer. So that's technical, but we're implementing these things here to access the data. And we're also implementing some of these or allow access through standard protocols like TAP. So the high-level goals, you could formulate probably in just 3 or 4 sentences. One is to enable easy exploration of very large data holdings. So like I mentioned, catalogs, pixels, spectra, survey file collections, anything you can imagine that goes with big data. But it's important also not just to provide access to them, but also to enable you to connect various data products. So for joint analysis, you might be interested, for instance, in AGN physics. I'm an AGN scientist, astronomer. And so you might maybe want data from an infrared survey, but also data from optical surveys, and you want to combine them together. So it's necessary to do that. One scenario could be, for instance, you make a complicated query, matching catalogs and so on. In the databases, you have now your finely tuned collection of the object that you're actually looking for. And now you want to find good images or good spectra on them. So you would actually combine these data products and be able to find them in Data Lab. And of course, like I mentioned before, now you need to be able to also execute remote analysis or run code and your algorithms on the big data that we have next to the data. So you don't have to download the data at all. You just have to upload your code and program there. And so for this, we provide a notebook server, a powerful machine that is shared between the users. And you can run as many notebooks as you like, as long as you like. I mean, with some limits, but you can always save your work and come back later too. And finally, we're thinking big about enabling easy user collaboration. So for instance, nobody works alone anymore in astronomy. You might be working as a part of a bigger project. And for instance, you are making a selection of sources, you're making a recommendation to the team. You could, for instance, then share the tables or the results or the CSV files or the catalogs that you created using the analysis here with your colleagues. So we provide, for instance, methods to share files, any kind of files in your personal remote file storage. If you put them in a public subdirectory, people can see it and you can give them a link to that. We have bigger plans here in the future that people can actually create groups ad hoc, separately administer them. It's not implemented yet, but the idea is that if you have an idea for a project, you start a group. This group gets a new username, if you want, at Data Lab. And you can then invite your colleagues and say, I want you to be in this group, and you have permissions to read and write, you have permissions to read, and so on. So this is something for the future. So maybe to show you quickly what kind of data sets we have in the catalogs. I don't have a whole list here because it's a bit long, but we started with the intention in 2017. I mean, actually the idea was born in 2014, but in 2017 we went online with the first version of Data Lab. The idea was to support the dark energy survey. At that time, it seemed like one of the largest catalogs available on the horizon. And so we were worried of how we will serve those data, not just images, but actually the catalogs. And so Data Lab was born with that intention. But by now, as you see, maybe here, if you can read those names here, that the dark energy survey, even the data release 2, it's not even the largest catalog now. And it's just one of many, maybe 20 or 30 big catalogs that we have right now. And so we're hosting now all the major catalogs from surveys that have been conducted with NOIRLab telescopes, but also external catalogs that are very useful for joint analysis. So for instance, UNWISE for infrared and ALLWISE, Gaia, of course, for astrometry, SkyMapper, the Australian telescope, and many, many others, and of course some spectroscopic catalogs as well. And so you see this logarithmic scale here, how many rows are in those tables. These are particular tables, not just the whole catalogs, but tables and catalogs. And so the largest is right now the self-made. We made it ourselves. My colleague David Neidova was the PI. The used to be called NOIO source catalog, but now it's the NOIRLab source catalog. Luckily, the letter didn't change. Data release 2 already. It's a re-reduction, homogeneous re-reduction of all the publicly available data in the NOIRLab archive, coming from 3 or 4 different telescopes and I think 3 or 4 different cameras. So of course the cameras have different effects, instrumental effects, different calibrations. So this is all taken care of there, so that you have now an access to a catalog where the measurement table is 68 billion rows. It's one of the largest actually in the world right now. I think ZTF has a larger one, but only in 2 bands, of course. This has 5 or 6 bands here. So this is 68 billion measurements of 3.9 billion sources. So really almost 4 billion individual sources. It's really a phenomenal kind of catalog. And because it's over 10 years or so of archive data, some areas on the sky have actually many epochs, hundreds of epochs in there. So the total volume of all the catalogs, these that you see plus more, of course, we're approaching close to 100 terabytes right now, just in catalogs, not counting images. Here's, by the way, an extra slide for the NOIRLab source catalog, NSC. So this is in data release 2. You see the coverage is almost 3/4 of the sky. And the column up here corresponds to the logarithm of the number of objects per square degree. And so you see, of course, the bulge, the disk, and the Magellanic clouds here as well. So it's a catalog that covers, like I said, 35,000 square degrees, 6 bands here. I mentioned this already, and it goes pretty deep in some bands, down to 23rd magnitude. And it's also quite very accurate. The astrometric calibration, thanks to Gaia, is better than 2 milliarc seconds. and the photometric calibration is 1 to 2%, so state-of-the-art actually. DR3 will be coming mid-22, I think, according to David and his team that are working on it, and will for the first time include PSF photometry, so should be even nicer data set. So back to our high-level goals. The first one was, of course, enable data exploration, data discovery. And here's an example of, for instance, how you might go about it using visual exploration, right? I don't know if some of you maybe have attended the AAS meeting, virtual meeting that happened this week. And on Monday, there was a special session on visualization in the era or in the age of data of science platforms. And so I showed the same slide there. There are various ways of visualizing the sky, right? The most popular thing is the Aladdin Light tool or Java servlet, JavaScript servlet that you can use on your website. And this is taken from our website, where as a survey footprint, I've selected, I don't know what it is, an all-sky image of maybe Gaia. And then you can zoom and pan it as you like. Here I zoom, for instance, on the LMC. And then you can overlay catalogs. So for instance, here I'm overlaying just by a click the fields, the observed fields of the SMASH survey, the survey of Magellanic stellar history survey. We would like to do a little bit more with that. So, sometimes we don't have the resources to do more. So things wait a little bit longer. But in principle, the user should be able to overlay any catalog of their choice, even upload their own catalog and see what they follow in the sky, and also select any kind of background, not just this one. There are others available. We are and have been looking at other tools as well. I just mentioned a few here, the Legacy Sky Viewer that came out of the Legacy surveys Legacy survey in preparation for DESI. The Subaru Hyper Supreme Cam Map is a very nice app, of course, but tailored for a particular instrument. ESA Sky, very powerful, has a lot of features and functions, also based on Aladdin Light. Rubin LSSD are developing Firefly that they will be using. And of course, there's the Worldwide Telescope, including the Python version for that, which is also very nice. And there are others as well, so I apologize if I missed a few here. That was not intentional. Okay, so next, once you have explored data, how do you get to the data, right? So I mentioned already the catalogs. We expose them through standard protocols, TAP protocol, table access protocol from the IVOA. So you can use any client that understands TAP, for instance, Topcat. And we support two flavors. You can use PostgreSQL, because the backend databases where we store our catalogs are Postgres, but it's it's very, very standard SQL. There's only a few specialties there. But we also support a subset of ADQL, the Astronomical Data Query Language, that also came out of IVOA. It doesn't support many of the geometric functions, but it supports the basic queries, cross-matching and stuff like that. We support both synchronous and asynchronous queries. So synchronous is if it's a short-running query, a few seconds to a few minutes, you can submit it, wait for the result, it comes back to your notebook, you can work with the data immediately. But some queries are, of course, much, much longer. They run for hours or even for days. And then you can submit such a query using asynchronous mode, where when you submit it, the return value is not the result, but also just a job ID. And then from time to time, you can check on the status of the job ID. And if it says completed, then you can download the data. And we have also a bunch of example notebooks for our users available in their accounts and on GitHub. So there's demonstrated how you can do that. It's quite easy. It's really literally just saying async equals true, and then making sure that the return value that you expect is just a job ID. Using both of these, you can query both the Data Lab catalog, so the 100 terabytes of catalogs I mentioned, but you can also query the same way your personal database. Every user account comes with a generous allocation of database storage, I think 250 gigabytes, and it's even a soft quota, so you don't have to worry about it. And the same for file storage. But using this kind of same protocol, you can just say, select everything from this table in MyDB instead of Data Lab databases. And like I mentioned, we support various clients, so Topcat or any kind of other tab-aware client. We have an own query client Python module, which you can load in the notebook or load locally if you install it. And I hope you can read it. It's literally you just write a SQL query string like select array and DEC from this table here with a limit, of course, and just run the query, and that's it. The result comes immediately. You can do the same thing on the command line, like I said. There's a little tool. It's really just a wrapper around those clients. And if you inclined to, you can also run some queries from our website. But again, I would just recommend it for quick tests. It's much more powerful and also more performant if you run it in a notebook or through the client. Good. Once you get to the catalog data, like I mentioned, you can stream them back to the client immediately. You say, select star from Gaia DR2, Gaia source, and it comes back to you. So it might be a very big table if you're not careful, if you don't select carefully. But you can also say, I want to output it here with the out parameter, either to a table in MyDB or to a file in VOSpace. So it'll be a CSV file if it's validated. And then you can, if it's a big one, for instance, you can output it directly to MyDB. And so you have it. It's basically like a snapshot of your query, of your workflow. And later you get back to it and use it for other analysis, for instance, for cross-matching. If you save it to a file, you can share it, for instance, with others. You can say, I made a query that was complex and I figured out some, how to select some particular type of sources. And then I want to tell Rodrigo, for instance, to look at it. So I would generate that file directly in my VOSpace and give Rodrigo the link, and you could look it up there. For convenience, we have some format conversion on the backend. If you say you want a different format than the standard CSV, you can also say I want to the return value be a pandas data frame. You just say format equals pandas, and what you return is a pandas data frame, so you can work immediately with pandas in your notebook afterwards. And we also support VO table, AstroPy table, a simple NumPy array, or NumPy record array, which has the header information still in there. I think most people, like myself, I use CSV or pandas most of the time. These from time to time if I have particular need for this application. Okay, and the final thing about catalog data here, it's very important on the backend for us to make the performance of queries fast, because it's not just one user or two, right? It could be several users. Especially during your workshop, during presentations, or during when somebody is running a grad school class and they introduce Data Lab, then they have 30, 40, 50 people hitting the system at the same time. So we have some optimization in Postgres in the configuration, but otherwise it's not a own compilation or something. One could even get 2-3% of performance if one compiled their own Postgres, but that didn't seem worth the trouble. But there are some configurations there that can make it faster. There's some optimization in the tables, for instance. All the columns that we think will be queried often, R-index, for instance, magnitude columns, and so on, they're indexed. If a column is indexed in a database, a big query against it can run orders of magnitude faster. So it's very important to be careful about it. And sometimes we discover either that we had a bad index or that we forgot an index, and people are querying for it, and we're complaining that the queries run slow. It can make really the difference between completing something within a day or not completing it. So that's very important. There's also things like, it's maybe too technical, but it matters how you order your columns in the table. The largest should go first and the smallest should go last. That improves performance as well. And then the biggest change and the biggest benefit we got, the biggest bump in performance, when in 2019 we first started introducing SSDs to database machines. And here's just a comparison plot, relative comparisons, the relative scale. How fast or how many queries we could run on the previous system comfortably versus the new system with SSDs. And for instance, you see this, the speed performance for positional cross matches, so really cross matching on the sky based on position. It's a 1 to 29, 1 to 30 ratio. So it's really that jump. Also because the machines have, are rated and have other parallelizations in there, the number of big queries that can run in parallel went up by a factor of 2. So something like 7 or 8 to now 15. That we think like we are still at 15 big queries, we are still bounded by CPU, not by I/O, which is really a good place to be at. Because if you wanted to go faster, you just buy faster CPUs. And so that was a great move. We just bought a third machine because with 2 machines, one was a production machine, the other was a standby. But it was really a bit of a nightmare to ingest new data sets because you have 2 machines in production, right? With 3 machines, it's easier now. One is production, one is a standby, and you have a third machine for yourself to do ingestions. Because new ingestions usually don't happen once. You ingest once, you do QA, you find something bad, you have to do it again and again and again. After 3-4 times, it's maybe ready for production. But doing that on a production machine or even on a standby machine was a bit chaotic sometimes. Good. So now that you have catalogs, one thing that everybody wants to do is connecting catalogs with catalogs, so cross-matching classical. And so we have, like I said, the Python API in Jupyter Notebook where you can do this. It's really a join because we create something called the Q3C index, so quad 3 cube. It was developed by Sergei Koposov and I forgot his first name, Batunov. Luckily for us, it is a plugin for Postgres databases, so we can actually just install it on our Postgres database and it works. And when you ingest the data set, you create this this index on array and deck once, and then you're good. And then the queries are very, very fast, meaning you can say, I want everything around this position on the sky in this catalog within 2, 3, 5 arc seconds. And the result usually comes back in very fast, in just a few seconds. And we expose this kind of mechanism for cross matches also on the website. There is a tool here. I wonder if you can see my website, sorry, my other tab. Rodrigo, could you confirm if you see my other tab?
Yes, we can see it.
Okay, great. So let me just show you, when you go to the Data Lab website, it's like that. There's lots of information about the data sets we have and so on. I'm not going to introduce everything. But if you go to the crossmatch service here, and I think it will ask me to log in, because it requires, the login here is required simply because it uses your MyDB to do fast query on the database backend. So if you have an account here, and by the way, accounts are free and always yours, so I invite everybody to come and get an account. It costs you nothing. So once you log in, then you see this kind of interface that I also have on my screenshot. And you literally just select your table, and you can upload tables as well. If you don't have one, you select one of our tables, big ones. You select the search criteria, submit, and you get the file back in seconds. So I'm not going to show it, but this is basically this screenshot. So I actually prefer sometimes to use this because it's so easy and it's kind of guiding you. You select one, it takes a second, and it says, okay, now tell me which are the columns that you want to cross-match on, array and deck columns. And then you select the second one, and it tells you the same thing. And then you literally hit the button, few entries, and you get the file back. Whereas if you do it in the API in a notebook, you have to code a little bit, and you have to look up the example and make it work. So this is actually very easy for the user. Probably, I would say, I don't know how to quantify it, but it's much easier to use. Okay, now of course you think, okay, now you have hundreds of users coming over the time, and everybody wants to do cross matches. Of course, everybody will want to do the same cross matches. Most people would want to do a cross match against Gaia for astrometry, or against another photometry catalog like the NSC, or against spectroscopy telescopes, spectroscopic data sets like the SDSS. So the idea was born that the use cases probably 90% of are the same data sets. Why don't we pre-compute cross-match tables for our users? And so, of course, some choices had to be made. First, what data sets do we cross-match against? We cannot cross-match against everything. Everything against everything would just be exponentially, would grow exponentially our data needs, storage needs, so we cannot afford that. And also, most of the data sets or the cross-match tables produced that way would probably never be used. So you would produce terabytes of data that nobody would ever access. So we decided on a few high-value, large data sets. So for astrometry, we use the latest Gaia release, so currently Gaia EDR3. Some of the tables, of course, still have Gaia DR2 because we did not recreate them yet. But we're waiting for Gaia DR3, the full DR3 coming out next year, and then we will redo them. So every new catalog ingested will be by default cross-matched against Gaia latest version. It's also by default cross-matched against the NSC, the NOIRLab source catalog that I mentioned before, and against Unwise DR1, so for infrared photometry. And for spectroscopy, we're using the latest SDSS, SDSS4, if you want, but this is currently version 16. And of course, if SDSS5 data become available, we'll change that too. And of course, we had to make a choice about the default matching radius. So it's 1.5 arc seconds, should be on the safe side. I don't know how well it works in crowded regions, but in not too crowded regions, that's a good matching radius. And we only keep the nearest neighbors, and we don't return the rows that had no match. So some common sense assumptions here is to make it easier for the user. And the tables are always the same form. So there's just the one table ID of the object, the array index, and for the second one ID2 array deck for the second table, and the angular separation between them. And then, of course, it's very easy for the user to immediately find from the name of the file, of the cross-match table, sorry, what is in this table. And so why we did this is because now if you want to cross-match your catalog against, let's say, a cross-match table that already exists, it's just a join on the database end. And the join is many, many times faster than a real cross-match on the sky, because cross-match has to compute trigonometry on the fly. It's very expensive computationally. This has only to do a join, and really in seconds you get the same results if you're happy with the default solution, with the default assumptions here. And like I mentioned, when a reference data set gets updated, like the idea 3, we will update all the cross-matching tables as well. Now let's go to the next step. If you have catalogs and you also can cross-match already, sometimes you would like to now connect the catalogs with the pixels that generate where the catalogs came from, right? Here's an example I show, for instance, the Go Green survey that I mentioned before. It was produced with Gemini telescopes and is hosted at Data Lab. And so you can set up a simple image access service, SIA, just using the proper URL for this data set. So every form is like that. And I apologize, this is to the old address. We are now on noirlab.edu/SIA/name of the survey, Go Green DR1 in this case. And then you can search, for instance, say, give me the R&D around this R&D positions in this field of view in 2 dimensions. Give me everything you have. Everything you have means it looks up in a metadata table the information for the images that we have in the archive. And the result, the returned result, is a table of images, including all the metadata. And then you can further sub-select and say, okay, give me only the images in the G-band, for instance, or only in the G-band with exposure time greater than 30 seconds. Or all that plus it has to be a science image, reduced science image, and not a calibration mask. And then in the end, you find the image you want and you can plot them here. So here is an example you see from that Go Green survey, something like 721 or so snapshots of galaxies and galactic clusters obtained from the data using the SIA search. And really the query is just a query against a table of metadata. The result contains a column called access URL, which really has the link to the particular image. And if you say also you want this to be a cutout with a given size, then it generates the cutout on the fly and returns to you the snapshot, the stamp image if you want. So it's quite useful for purposes like this. Good. I mentioned before, so I kind of jumped ahead of myself. If you create a new user account, so just really go to datalab.noirlab.edu and click on sign up. We ask for your email and your name and institution, that's all. And then an account is created for you, which has by default 1 terabyte of storage on the remote VOSpace. So this is yours forever to keep. And again, like I said, it's soft quotas. So if you need 2 terabytes, you'll be able to use them until, unless everybody would use 1 terabyte, we would have to enforce quotas. But most people are not using that much at all. And so meaning we don't have to enforce anything. If you have a need to use 2 terabytes, that's fine. You can access then the data. If you have an account, you can read write to this storage space. Because many of the things you can do anonymously, by the way. You can run a notebooks query against our data sets without an account. But if you want to store notebooks, save them, come back later to them. If you want to write something to MyDB or to VOSpace, you need an account. Otherwise, of course, they don't exist. And as I mentioned before, in your VOSpace, which is the remote storage, there is by default a subdirectory called public with permission sets set such that whatever you put there is visible to other data lab users, and they can download it from there. So it's a very easy way to share files or collections of files. And the VOSpace is also visible in your Jupyter notebook that runs on Data Lab servers. So there is basically on the left when you have the files, you can just click on VOSpace and you see the files in there. It's a read-only link, but it's very useful. And in the same fashion, like the remote file storage, we also have Postgres databases for you. Again, we say 250 gigabytes, it's just an estimate, it's a soft quota. So you can either upload your own CSV tables or any kind of tables to MyDB, or you can create MyDB tables as a result of queries against our big tables. And just say, I sub-select on a big table and I want to dump it into a table in MyDB for later usage. So it's the same, works the same way. And again, you can rewrite tables, you can drop tables, it's your database, you can do whatever you want with it. And again, you can access it through a query client in a notebook or from your home computer, or even through the Data Lab command line client from your computer. If you use this command line client, of course, you're losing the co-location because you're working, the data have to be transferred between you and your computer and Data Lab. The MyDB is also, I mentioned before, is used internally for the fast positional cross-matching because the database knows how to do a join very quickly. So if you want to cross-match some own catalog against, let's say, Gaia, you could upload it to MyDB and then say, and now cross-match this table in MyDB with Gaia, and it works really within seconds. So almost done here with the features. I mentioned the file service before, where a survey team creates a collection of files that they want to expose to the public. And what it really is internally is just a VOSpace, but that is only read-only and that is public. Everybody can see it. So really, that's literally the same technology, just with 2 flags set. And so this exposes any kind of data collections, file collections, sorry, to the users. It's a very easy way. You can put anything in there, FITS files, catalog files, documentation, even scripts and auxiliary files, and you can access them again through a store client. Literally, you can download the data or browse them as you like. It's very easy to use. So I mentioned before spectroscopy. So this is our next step. After all the large photometric catalogs that are out there and the images that we can access, now we're getting ready for the era of massively multiplex spectroscopy. And so currently, probably the largest spectroscopic data set is SDSS with the various data releases, and also SDSS-5 just started. But also now DESI has started, the dark energy spectroscopic instrument. I've mentioned that they're collecting data for the main survey since 1 month in Cape Peak in Arizona. And I heard just a few days ago that within 1 month, they collected 1 million spectra of galaxies, including determining the redshift. So this is really at the level of doing 1 SDSS in a few months. It's an amazing machine, and it will produce something like 35 or 40 million galaxy spectra by the end of 5 years. And of course, for the future, there are other big surveys, wide field surveys with many fibers planned. The Mauna Kea Spectroscopic Explorer, MSE, Phobos at Keck, and potentially others. The issues currently, of course, if you want to serve spectra, you usually put them in FITS files and you open them. This is painfully slow. It does not appear painfully slow if you want to open one particular spectrum, right? Opening FITS file or something in a notebook is 1 second. But if you want to open 1 million spectra, that's unacceptable. Even parallelization will not help there. There's lots of overhead in file I/O when you're dealing with FITS files. So it's not feasible if you have many spectra like coming out from DESI or other surveys. So the idea was that we need to develop some kind of fast access spectroscopic service at Data Lab. And how do we potentially enable people to query for thousands, hundreds, thousands, even millions of spectra at a time? So I introduced DESI a little bit already. So the instrument was put on a retrofitted 4-meter class telescope in Arizona, the male 4-meter telescope. The DESI survey will survey something like 14,000 square degrees in the sky, produce 40 million spectra of galaxies and quasars, including 10 million of stars in our galaxy and nearby galaxies. Commissioning is completed, and the 5-year survey started already. So this is, I need to update the slide. Sorry, didn't want to go. Yeah, and so you see it goes also bright, and it has pretty high resolution, and also serves the spectra in 3 different arms, red, green, and blue. So it's a complex data set as well. Here's a science example what you can do with that. This is currently using SDSS spectra, but it's a prototype. It's a notebook that was developed by one of our summer students that work with us, Raga Pucha. Where you see, maybe if you're working with galaxies or AGN, it's familiar to you. This is the BPT diagram, where there's 2 line ratios on here, and galaxies or galaxy type fall in different regions colored here. So some of them are just normal galaxies, some of them are star-forming galaxies, some of them are AGN, and so on. And the idea was, okay, science example, could we select a random number of galaxies from each patch, those little squares here, or put the patch randomly somewhere, select 100 spectra, say, retrieve them and stack them for better signal-to-noise ratio. And you see this stack spectra here. I think this is, sorry, single spectra. These are stack spectra here in those different areas. And so the first notebook that was written to demonstrate this was accessing the spectra, the SDSS spectra, from the FITS file that they came from on the back end. And even though we have fast machines and the notebook runs on in the same data center, executing this notebook where you query just 400 spectra by opening FITS files, loading them, and doing the stacking takes 7.5 minutes. But once we have the first version, it was really at the time still a prototype of the spectral access service, the same notebook executes in 25 seconds, and only 8 seconds are needed to get the spectra actually out of the system. The rest is spent in creating plots and saving the notebook. So how do we do that? The prototype uses cached versions of those SDSS spectra, where the spectra have been extracted from the FITS files and put into binary arrays, NumPy arrays on the backend, and they're in a fast SSD cache as well. And all the metadata information that comes with the spectra, of course, it's in a database. So when a user queries for particular properties, they get as a return value the list of IDs, unique IDs from SDSS that corresponds to those objects. And then you can feed the list of IDs to the Spectrum client and say, retrieve those spectra for me, and please give me both the flux and the inverse variance maybe, and so on. So you can also ask what kind of components of the spectral products you want. And only those are returned to you. So by separating the metadata out from the data, we could put the data in a fast binary format and in a fast storage. And you see the order of magnitude increase in performance here. So this is still maybe not suitable for millions of spectra, but it's very suitable for thousands, if not hundreds of thousands of spectra. And so this was a prototype, is in production now. It's a demonstrator if you want. We are using the lessons learned from that in developing a new production level system that can do the same thing, but can scale to the level of DESI, which is orders of magnitude larger than SDSS. And so DESI is the first thing we support. I think the first DESI data release will be early next year, but of course we need to be ready a bit earlier internally because the data set will be frozen at some point later this year. I think in September or so is the current plan. And so at that time we know what the data format looks like, it's frozen, and we can freeze the system as well, and then get into demonstrating it, testing it, but also optimizing performance. Good. Like I mentioned, the idea of a science platform is that you bring your idea and your analysis, meaning your code, your notebooks, your libraries, anything you want to the data, instead of downloading anything. And so that requires that you can execute remote code, and the current gold standard for that, for most people actually in astronomy, especially since Python is so popular in astronomy, is to run it in the Jupyter Notebook server. And that's what we also provide to our users, a Jupyter Notebook server with a Jupyter Lab interface. Since last year, we updated to Jupyter Lab, which has some number of nice features here where you can split the screen, for instance. The benefits are, of course, many. There is no installation of software required from the user. All you need is a browser, a Data Lab account, and internet connection. To get users started, of course, we want to demonstrate how to use a Data Lab using the notebook. So one of our big things that we do constantly, the scientists on the team, but also the engineers, are developing and improving notebooks, example notebooks. So we have a large suite of notebooks that are made by Data Lab people and colleagues and contributors. Something like, I think, 50 notebooks right now, plus some additional ones for educational public outreach that are all publicly available on GitHub. But also, if you create a new Data Lab account, at the time of the account, we make a copy of those notebooks, the current state, the latest and greatest, into your directory. So when you start up the notebook, Jupyter Notebook server for the first time, you will see all your notebooks here in a nice collection. And they are ordered by category. So there are introductory notebooks, technical notebooks, scientific cases where you see an entire science case from idea to final data, and also educational public outreach. And there is also a contributed notebook. So we invite everybody who has a good idea for the notebook that you've done with Data Lab. You can make a pull request on GitHub for that. We iterate with you a few times until it has the same standard, the same format as our other notebooks, and then we integrate it into the suite. So that's actually very welcome. And the entire astronomy software stack is installed by default, meaning you can count on AstroPy being installed, NumPy, SciPy, scikit-learn, visualization tools, Matplotlib, Bokeh, all that stuff. If there is a library that we don't have, you just ask us and we test it, and usually we install it within a day or two. This is, of course, easy on one end to maintain. On the other end, also, of course, it makes the stack a bit bloated. Most people don't need all these 20 libraries installed there. They need only 2 or 3. So we currently planning and developing a little bit in containerizing our Jupyter Notebook server, orchestration with Docker containers and Kubernetes to orchestrate them. And in that sense, then, rather than sharing one big machine, every user coming and launching an instance will just select an instance. I want 2 CPUs and 8 GB of RAM or something like that. And the container that is then spun up and run for you is yours. So if you want to install a package there, you just do it yourself with pip install, and it's yours. And you can delete it also, or you can start from scratch by saying, drop this, give me a new one. It should be easier for us to maintain, but it should be also more flexible for users who know what they want and who want particular packages and don't have to worry about us. We want to install it, but sometimes it takes a while because we need to test first whether it interferes with other packages and things like that. So that's in progress. Hopefully next year sometime we'll have containerized notebooks. Right now it's a big virtual machine, big dedicated machine shared by many users. And of course, in Notebook, we exposed interfaces to the data. So like I mentioned, the Data Lab query client for queries, store client for accessing VOSpace, and also there's an authentication client for login. So you can access all your data and our data through the Notebook. This is more about access modes and access protocols. Like I mentioned these already. We haven't settled on SSA, which is single spectrum access for the spectroscopy thing. It comes out of the IVOA, which would be good to support, but our impression is that it's kindly tailored more for single spectrum access. So it's really not the use cases we have in mind with millions of spectra, but we have to see how to expose this. I mentioned Postgres, I mentioned our clients, sync async queries, and Python API, so we don't have to go through this again. You see it's a sandwich by basically the user sees the front-end clients, they interface with middleware, and this actually gets to the data on the backend. A little bit about our plans for the future. For the next year, we have a plan to introduce finally the user-managed groups that I mentioned in my introduction. And so the idea is that we could create a group spontaneously on the fly. Anybody could do that. We can decide individually who we want to invite to this group. You know, 1 person, 2 people, or 50 people. That's possible. We can assign roles. So the administrator can say who is a co-administrator, who can read write, who can read only, and things like that. You can attach your own storage, or the group has its own storage attached. At any time, the administrator should be even able to destroy the group. Maybe it was a summer project, you don't need it anymore, you just say, and now dissolve this group, it's gone. And one idea is also that if you have a project, you could lock it at some point and say, we worked on a paper, this is the data we produced, this is the paper here we produced, now let's lock it, mint a DOI that you can give, for instance, to a journal or to a referee. The idea is not ours. This was actually implemented already at CADC in Canada with the VOSpace extended version that they have, which supports this capability. So it's literally a VOSpace where a bit is flipped at some point. You just say, this is now a minted DOI, so the data cannot be changed anymore. And literally you could send that. It's guaranteed then to preserve the content of the directory, and a referee, for instance, could review it. So that's something we want to incorporate in Data Lab. So I'm coming to an end here. What I also consider a service, not a data service, but the user support is very important to us. So like I mentioned, if you are interested, please join us, get a free Data Lab account just by going to here, datalab.noirlab.edu, click on sign up, and that's it. You have an account within minutes. And whenever you have questions, I forgot the dot here, by the way, that's noirlab.edu. You can shoot us an email to this email address, or you can go to the help desk. The help desk is literally just an FAQ. You can search for previous questions there. You can post your new questions. We answer them all the same. The benefit here is that other users will see a previous solution to a problem, right? Often it's a question. Any question, by the way, is possible. So from this doesn't work the way you said it would, or something seems broken, or can you help me with my SQL query? It runs very slow. Or how would I find images for this in the survey? We answer any question there, and all questions. That's our goal. So the benefit here, of course, that other users can see the solution later and benefit from the lessons you learned. We have a user manual that is never complete and always updating, but lots of stuff is there already in. So that's basically just Sphinx documentation, but it exposes. It's very nicely organized and has many good tips and advice for using database. Our clients are in public repositories on GitHub, so you can feel free to take them and build something better with them, of course. And I said the notebooks are exposed as well, so you can find them in this repository or in your account if you have one. We also have Twitter. We don't use it much, but sometimes users actually do ask us something on Twitter, so that's nice, actually. A nice opportunity if you prefer using Twitter. And finally, like I mentioned, if you want to use it if you want to use Data Lab, making queries, for instance, from your local computer, you can do that by just installing the Data Lab command line client. It's still called NOIRLab Data Lab. We haven't changed it yet. Just using pip install NOIRLab Data Lab. And so I think this is my final slide. The 3 things to take away from my talk, I think, is that a science platform, other than an archive or in difference to an archive, it combines big data with collocated remote compute. And it makes data discovery easy, data access easy. It provides features for analysis, visualization, reduction of data if you want, and also for collaborative working. And the Data Lab Science Platform is just one component of the entire NOIRLab data ecosystem. It does all these things, and also we're hosting at the same time one of the largest collections of photometric data, image data sets. So these are all publicly available data. These are all open data, and we are, making a big point or proud about this, providing access for the community at no cost, for free, and are big on getting people together so that any idea that somebody has should not depend on whether they have the resources to pursue it or to make science with it. If you have access to an internet connection, you can have access to terabytes, hundreds of terabytes of data, and your idea is the only thing that matters. So that's a very important mission for us. And like I said, we are a community science platform, so we care about our users. We try to use open source. I mean, we use open source for everything that we have. We try to be open access for most data sets. Sometimes we ingest a data set before it becomes public just to play with it and just to prepare for it, but eventually it becomes open access. And we try to support open standards where possible. So IVOA, what's possible for interoperability. And only sometimes we invent things if there's nothing on the market, if you want, that suits our needs. And so I stop here. Thank you very much for your attention. It was a pleasure being able to talk to you. Thank you.
Thank you very much, Robert, for the very remarkably interesting talk. We now have some time for questions from the audience. If you joined us on YouTube, you can put your question in the comments section, and we'll redirect your questions to Robert. If you are with us, if you joined Zoom, you can ask yourself, raise your hand. So questions? Okay, while we wait, I'll ask some questions. I saw my doubt concerning the catalogs that are available in Data Lab. It looks like, are they only co-ed catalog, or are there some single epoch catalogs to do time domain science?
There are several single epoch catalogs. So, for instance, in the largest one, the NSC DR2, right, there is a measurements table as well. That's the big one with 68 billion rows. There's also a single epoch data in SMASH, in DCAPS, I think, the plane survey with the dark energy camera, and several others. So not all, of course, but several others, right? We're ingesting right now VHS, which I don't think has single epoch data, but S+, which does. And so it depends really on the data set that become available to us. Okay. But for instance, there are also notebooks, like I mentioned, in the notebook collection that we expose to our users. There are some examples that show time domain science. One is, for instance, getting data, time resolved data for a particular RLR star, and then constructing the light curve from the time series. And also, if you're familiar, maybe, or you're working on alert stream or alert brokers, one alert broker developed also in Tucson is called Antares, which is currently serving ZTF data. But it's the ZTF data is preparation for the LSSD, of course. And so we have 2 or 3 notebooks that showing they expose the Antares alert broker client in Python, which you can then load, and you can start playing around by developing your own filters for that stream, including instructions how to make that. It's literally a Python function. Say I'm looking for I don't know, any kind of event that happened within the last, when you look back, will change in magnitude within a week, and of that in that magnitude, right? 1 magnitude or more, or something, like if you're looking for supernovae. So plus 2 notebooks there that show actually this kind of client in use.
Okay, that's nice. Thanks. Questions? More questions?
Can I ask a question?
Okay. Ask your question now, and then Julia. Okay.
Okay. It will be quick. So in the website, you have the image cutout option, but you have only the option to download a single image, for example, a single fits file for a single object, right? So if I want to download the file for many objects, I have to click manually for each specific object, right? There's no option to download them all.
I thought there was on top. I thought that there was an option to click all and then download them. But if not, I'll double check. But if you wanted to download many things, I recommend the easiest and more performant way is actually to generate the cutouts using a notebook. Because then you can say, in a loop or something, you can say generate all these and then dump them straight to my VOSpace. You don't even have to download them. You can just put them in your remote storage in a directory that you created and can work from there. If you wanted to download them, you can also download them from the VOSpace to your computer very easily.
Okay. Thank you.
Sure.
Julia?
Yeah, thank you, Robert, for the very nice presentation. About the demonstration and notebooks, you already said that everything is open source, but could we use that notebooks in classrooms? I mean, for high school students to do EPO? Could we just open that inside a classroom and use that as an educational resource?
Absolutely, yeah.
Obviously, giving out the credits for.
So if you can use them in classroom using Data Lab, right? Either the students can get accounts. I didn't mention it, but if you, for instance, want to run a one-off class, like we do during the semester, once a month, the EPO group in Tucson, they run something called Teen Astronomy Cafe for high school students with astronomy. So those students come for one Saturday. Before COVID, they came to the building, but now they do it on a computer from home. They come one Saturday and they do a whole day of experimentation with the computer, for instance, exploring solar system, right, simulating that. But after that, they never come back, right? So we don't give them full Data Lab accounts. But what we do, we give them demo accounts. We have like 50 demo accounts ready that we reset to 0. And then they get randomly assigned demo accounts, demo 1, demo 2, demo 3, and so on. And they can play just the same. They use their account for the day. And after a week or so, after this activity, we delete those accounts again. So if you wanted like that, something like that, just talk to us. We do that easily. But if you want to have, for instance, a class that, students that work over a whole semester with them, then they should just make Data Lab accounts. There's no restrictions on who can make an account. Just have them make a Data Lab account, use them, under their own name, and then they can use them like a normal Data Lab user would. And then, so back to your notebook question, you can use those notebooks. You can modify the notebooks. But if you just want to get to notebooks and don't deal with Data Lab at all, you want to do it on your own, that's fine too. You can have the notebooks and take them from GitHub.
Great. We are working on the preparation of a course, a little course here for EPO. And if we are already preparing some notebooks, and if is there some subject that is not covered already in your notebooks, we will be glad to make a pull request and contribute a little bit there.
That would be fantastic, yeah. Because we have some science cases covered, but many that are not covered. So we'll be really glad to have a good notebook contributed.
Okay, thank you.
Thank you very much.
Thank you, Julia. I think we can have one more last question.
Hi, Robert. This is Adriano. Thank you for the presentation. And I'd like to know what is the total amount of, let's say, active users of Jupyter Notebooks?
Mm-hmm. So it's a good question that we try to monitor, right? We don't resolve or monitor where the users are making the queries from. So for instance, we don't distinguish between queries from a notebook or queries from the website or queries from your local computer. But in total, we have like rough estimates of how many users. So we know how many users registered an account. So today it's something like 1,700 people since 2017, right? But of course, not every user comes back. Sometimes they just try it out or they register for a workshop and then never use it. So what we do is that after a year of somebody having not logged in, we deactivate the account. We don't delete it, just we set a flag in the database saying inactive. And the user can come back and reactivate it again when they log in. But so based on that, we just know roughly for the current point in time, how many users are still active. And it's roughly 60% of the 1,700 are still active. And so I can also tell you the numbers, for instance, of how many users log in daily or weekly. So at any given time or any given day, I would say we have between 5 and 25 users on a day. That really depends. Using the notebooks or using the Data Lab in some form. And I would say, maybe something like 900 to 1,000 users who still have an account that is not inactive.
Okay, thank you.
You're welcome.
Thank you, Adrian. I have also a last question. You said that you told us that but when running when processing or running notebooks, everyone uses a one big machine. So are there policies like do not use too many cores? Sometimes you want to run something in parallel. What are the instructions on that?
Yeah, so we don't have any. I don't even know if there is a way to, if you're sharing a big machine, to limit RAM usage.
Okay.
Yeah, so luckily it wasn't a problem much. The biggest RAM users are actually Data Lab members when we're trying something big where that actually works or breaks. So most users, run a notebook that has, 3, 4, 5, sometimes 8 gigabytes of RAM needs. I've run notebooks that have, 20, 25 gigabytes for a while and then not. The number of cores that you can use, I think, is set to 4. So you can use 4 cores at a time.
Okay.
But of course, users have asked us, and just in case you're wondering, somebody else, can I make a second account and run 4 more? And yes, you can. We cannot stop you.
Yeah. Okay. Hope people don't do that.
a few. Somebody always tries to get more, but not many. So that's good, actually. Yeah.
Okay. Thank you. Okay. If there are no more questions, I think we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel, so you can access it later if you want. And for the next week's webinar, we will have Jacques Lepine from the Universidade de São Paulo talking about the role of the co-rotation resonance in the galactic disk and its influence on the sun and stars of the solar neighborhood. So thank you everyone for attending, and a special thanks for Robert. Thank you, Robert.
Thank you all very much. It was a pleasure to be able to talk to you, and appreciate the invitation. Thank you.
Yeah, thank you. So everyone, have a great day. Stay safe, and I hope to see you all next week.
Bye-bye.
Bye-bye.